AI minds, quantum leaps. Cut the noise, dive deep. Truth unlocked. Dr. Mike on the mic. Tech Unfiltered is on the clock. Now it's time for the show.
Mathematicians are having an unusually serious conversation about artificial intelligence. The easy headline is that AI has solved mathematics. That is not what happened. What happened is narrower, more complicated, and more important. Earlier this month, OpenAI published a collection called 10 Advances in Mathematics and Theoretical Computer Science. The company said an internal model called Astra produced 10 results that resolve or make substantial progress on long-standing open problems. Astra has not been released, so researchers outside OpenAI cannot test the model itself. These were not classroom exercises. The topics included high-dimensional sphere packing, error-correcting codes, graph structure, quantum game theory, high-dimensional search, and a question about non-Sophic groups. Some are mainly theoretical. Others connect to practical problems such as reliable data transmission and security in a future with quantum computers. Sphere packing asks how efficiently objects can fit together when mathematics extends beyond the 3 dimensions we experience. That sounds abstract, but related structures can influence how information is represented. Error-correcting codes help recover information when a signal is noisy or incomplete. The collection also addressed questions about when patterns must emerge in complex networks. These examples matter because they were problems active researchers recognized as serious, not puzzles created only to make an AI system look capable. OpenAI released more than 250 pages of technical papers, plus about 60 pages describing how the ideas developed. The proofs were also formalized in Lean, a program that checks whether a mathematical conclusion follows from the stated assumptions. You can think of Lean as a compiler for mathematics. A proof either passes the logical checks or it does not. That verification matters. The Verge interviewed professional mathematicians, and the broad response was that the work has genuine mathematical weight. Fields Medal winner James Maynard described the results he examined as very impressive, while stopping short of calling them conceptually transformative or worthy of the field's highest prizes. Other researchers said AI's usefulness in professional mathematics appears to have entered a new phase. One researcher told The Verge that solving a single problem of this caliber could help establish a human mathematician's academic career. Producing 10 at once therefore attracted attention even from people who were cautious about the company's framing. At the same time, a proof checker answers only a narrow question: whether the formal steps follow. It does not tell us whether the result opens a productive new field, whether the chosen problem was the most valuable one to pursue, or whether the explanation gives proper credit to the earlier ideas that made the proof possible. The capability is also uneven. The same class of technology can contribute to an advanced proof and still make mistakes in elementary arithmetic, dates, or time. Mathematics is not one uniform ability. These systems appear strongest when they can combine known ideas, search many possible approaches, and receive a clear signal that an answer is valid. In this case, formal proof checking provides that signal. This suggests a broader principle. AI can be used more confidently when its work can be checked mechanically and reviewed by experts. That does not mean the system is generally reliable. Success in a formal proof does not show that the same model can reliably diagnose an illness, judge conflicting evidence, or understand a difficult human situation. There are also major limits to what we know. Astra is private. OpenAI has not disclosed how many questions it tried or how many failed attempts came before the 10 public results. That missing denominator matters. 10 successful results could reflect a highly efficient system, an enormous search process, or something in between. OpenAI estimated that generating the successful work would cost about $2,000 at current application programming interface prices. That is not a full accounting. It does not include the cost of developing the model, the work of expert mathematicians, failed attempts, or the process used to select the results for publication. Humans were involved throughout. People chose the questions, guided the work, interpreted the output, prepared the papers, and built the scholarship on which the new results depend. The accurate picture is not a lone machine making discoveries without help. It is a new research system in which human judgment and machine search are closely connected. That connection led to a dispute about credit. OpenAI's original announcement said the problems had seen no progress on their main result for at least a decade. Researchers Andreas Thom and Gabor Kuhn had produced relevant recent work used in one of the results. After criticism, OpenAI changed its description. The revised language says the collection resolves or substantially advances long-standing problems, and the company acknowledged that the proof relied on important prior research. The proof can remain valid while the public story about how it was produced is incomplete. Formal software can check logic. It cannot decide whether research has received fair credit. Attribution, disclosure, and professional responsibility remain human decisions. This helps explain why many mathematicians are reacting so strongly. Graduate students often learn by working through difficult but bounded problems. If AI can complete more of those projects quickly, universities will need different ways to teach proof, intuition, and research judgment. Take-home work also becomes a weaker measure of what a student personally understands. Mathematical progress is not simply a checklist of unsolved questions. A valuable solution often introduces a new concept, reveals a connection, or suggests better questions. Researchers interviewed by The Verge disagreed about whether current AI work is creating that kind of conceptual direction. Some see powerful combinations of existing methods rather than fundamentally new ideas. Others believe faster formal discovery could still give humans more raw material from which new theories and applications emerge. That distinction will take time to judge. The concern is not only about jobs, it is about how a field develops new experts. A 4-year doctoral project must be chosen with some confidence that it will still teach valuable skills years from now. When AI capabilities change quickly, that planning becomes harder. Access may become another dividing line. Mathematics has traditionally required far less equipment than laboratory science. A researcher can do important work with time, collaborators, a library, and a whiteboard. If frontier research begins to depend on proprietary models, well-funded institutions may gain an advantage. Research access programs and open-weight models could reduce that gap, but the strongest systems are not available to everyone. There is real upside as well. AI could help researchers search literature, test conjectures, formalize proofs, and connect methods across specialties. It could give students and researchers outside elite institutions access to forms of assistance that were once scarce. It may also move routine search and verification away from humans, leaving more time for choosing meaningful questions and explaining why a result matters. The near-term outcome is more likely to be a change in the division of labor than the disappearance of mathematicians. Machines may do more searching, combining, and formalizing. Humans remain responsible for selecting worthwhile problems, checking assumptions, recognizing conceptual importance, assigning credit, and deciding what should happen next. There are 3 practical lessons here. First, do not confuse a spectacular result in a checkable domain with general intelligence or everyday reliability. Second, verification should determine how much autonomy we give an AI system. Clear mechanical checks support greater use. Ambiguous evidence and human values require more caution. Third, credit and access are policy questions. Universities, publishers, and funders will need rules for attribution, disclosure, reproducibility, and fair participation. Artificial intelligence has not solved mathematics. It has produced credible, formally checked advances in selected areas with substantial human involvement and unresolved questions about reproducibility, selection, credit, and access. That is not a robot replacing an entire profession. It is a powerful new research tool beginning to change how knowledge is created, how expertise is taught, and who gets to participate. I'm Dr. Mike, and this is Tech Unfiltered. I'll see you next time.